Good morning, class. Today we're going to look at exponential and logarithmic equations. Now, we've already solved some exponential equations, and we solved some logarithmic equations in the previous assignment as well. These will be a little more advanced, though. And let's switch to my, there. So let's start off with exponential equations. We've already seen one method of solving. There are two generally accepted methods of solving exponential equations. There are two methods of solving. The first method, I'll Roman numeral it. Roman numeral 1 is the same base method. We were looking at that 1 week ago today. And we said with the same base method, let's see, this one right here. Oh, well, what about, let's see, I think I had a real basic one to start off. With the same base method, if you have the same base on both sides, then the powers have to be equal. And that was the job. The work was to get that common base. For example, 16, we had to write as 2 to the 4th power. We had the same base, so we dropped the base, set the powers equal. And with the same base method, we said something like this: 2 to the x equals 7. Can't be done. 7 is a prime number. There is no way you're going to write 7 as a power of 2. And so I said, for something where you can't get a common base, you will have to use logarithms, and that's what we'll be seeing today. So the same base method, I'll make a note, that was in homework assignment,
the 1 over exponential.
Yeah, okay, I'll say we saw that in previous assignment. The second method, the new method, if you can't get a common base, I'll say unlike bases. In that event, we're going to have to use logarithms. Now, you'll ultimately, if it's impossible to get a common base, your answer is going to be an irrational number. So you're going to be stuck with a logarithm in your answer that you're then going to have to punch into your calculator to get a decimal approximation. It's up to you whether you use your LOG key on your calculator or your LN key. I prefer the natural logarithm key. So here's what I'll do. If it has the equation as unlike bases, I'll take the natural log of both sides and when you introduce those logarithms for a moment, the equation looks even worse. You have an exponential expression and a logarithmic expression that you can then use the power rule to bring down the exponent. And to illustrate, once you bring down that exponent, then you'll just have to use your algebraic skills to solve for x. But to illustrate, let's look at number 1.
Last week, this looked different. Here, a week ago today.
I don't know what you're talking about.
This, the sidebar.
Yes.
Does y'all's look like this, or does it have that new look? Because ours went back looking like this after
one day, and we didn't change anything or do any change settings. Ours is back looking like the old thing, but it was like that on Monday too.
I know, and the new setting didn't say question 1 up here; it just said question, and that's what annoyed me the most. But so maybe they heard my complaining and.
Oh, I'm sure, Pearson. I am sure.
Artificial intelligence, maybe. Listen, AI.
Oh. Okay.
Do we agree there's no way we're going to get a common base?
3 and 5 are both prime numbers. No common factor other than 1. So there is no way we're going to get a common base. What we'll do, I'll introduce logarithms on both sides. ln, and I'm using my cursive writing to denote the natural logarithm. Otherwise, if I use, that's what the key looks like on your calculator, unfortunately, on some of them.
Yeah. Well, our calculator makes the calculator.
When you're typing it in, that's what it looks like. It looks more like a 1N or an IN, so I'll use cursive to make sure you realize that is a natural logarithm. So we take the natural log of both sides, then we use the power rule of logarithms to bring down the exponent. Well, there's only one exponent. We're going to bring it down. X times the natural log of 3 is equal to the natural log of 5. The natural log of 3 is a number, a messy decimal number, 1 point something or another. That's the best I can do. Yeah, but it's still a messy decimal number.
1.0986122289.
But that exact value doesn't matter now. But it's a variable times a number. We want that variable by itself. What do you do to get rid of, to undo the multiplication? Divide by ln3. ln3 is a number. We add x times a number to get rid of the number. To get rid of that number and get x by itself. Divide. ln3 is actually the coefficient of x. But when you do that, the ln3's cancel on the left, and what you have left is just x equals ln5 all over or divided by ln3. And they're going to want us to punch this into our calculator and get a decimal approximation. Switch back to the problem. How do they want the problem rounded? Round to 4 decimal places. So switch back to my work. And we put in ln. Notice it opened a parenthesis. Like I said the last time, you have to close that parenthesis once you type in the argument. So we have an ln5 now divided by ln3. Now if you don't close the final parenthesis, they'll close it for you and you won't have a problem on this model calculator. I know the old TI-92, you didn't close those parentheses, you had a lot of problems, syntax errors.
It says round to 4 decimal places.
So what are we getting? I'm going to put wavy equals to mean I'm using an approximation, 1.46497. That 49, is it going to stay at 49 or is it going to go up to 50? It's going to go up to 50 because that number after the 9 is a 7. If it's 5 or more, it goes up. If it's 0 through 4, it goes down for a final answer of 1.4650. And realize, if your calculator opens parentheses, then you have to close that parentheses around each one of the arguments before going on.
You'll notice that this solution is not a real number. That would happen if when you type in your answer, if you wind up with something,
say a -5.
Let's see, how about
why did you put in 2 parentheses?
Oh, I didn't mean to, did I? Oh, wait, no. Okay. I need to delete. If I punched this in, if this were an answer,
you'd get the non-real answer. But the real point is that if you punched in ln any negative number, say -8, remember, you get an error. That's what would happen if you were going through using your calculator and you wound up with the log of a negative number.
Then you would choose that answer that it's not a real number. And when else did we see that warning, error sign, non-real answer? If it's not a real number, what is it? An imaginary number. It's going to turn out that the answer would have to be an imaginary number. Well, are you my friend there?
Yes.
Oh, okay.
5 to the 2x plus 2 is equal to 3 to the x. Okay. Notice the exponent is more than just a single term. We'll still apply the natural log to both sides. And that's going to let us pick up that exponent and move it down and write it as a factor. But the entire ln 5 is going to have to be multiplied by the entire exponent, 2x plus 2, to make sure you realize that 2x plus 2, when you bring it down, the whole thing's going to have to be multiplied by ln 5. We'll write it in parentheses, 2x plus 2 times the natural log of 5 is equal to, pick up the x, move it down, so it's x times the natural log of 3. Realize something. When you introduce these logarithms, the way I'm doing this stuff, I had an argument of 5 and an argument of 3. I have ln 5 and ln 3. That's it. Your answer shouldn't wind up magically with ln 8s. It shouldn't wind up with ln 15s. When you're punching in your answer at the end, the only natural logarithms you should have involve ln 5 and ln 8. We have a number times 2x plus 2. ln 5 is a number. It's 1 point something as well, okay? But it's a number times 2x plus 2. What are we going to do to perform that multiplication? We're going to distribute, and we're not going to get creative. 2x times ln 5 is just 2x ln 5.
No ln 10.
It's not ln 10. It's not ln 10x. It's just 2 times x times ln 5 plus 2 times ln 5 is just a 2 ln 5. Don't make it an ln 10. Don't make it an ln 7. You start off with ln 5s and ln 3s. The thing you're going to punch into the calculator should just have ln 5s, and here we have an x ln 3. Those ln's are just numbers. They're messy decimal numbers. The coefficient of x is 2 times ln 5. The coefficient of this x here is ln 3. If you have multiple x terms, get all the x terms on the same side of the equation. I'm going to move these terms around in a way so as to minimize negatives. I guess my natural inclination is to get the x terms collected on the left. I think I'm going to do it on the right. That'll be less moving around, and there'll be fewer negatives then. I'm going to leave the term that doesn't have an x on the left side. So it's a 2 ln 5 equals, I have an x times ln 3, pick up this term, move it to the right. That's an assumed positive. If we move it over, it's going to become, so we have a minus 2x ln 5. If you have multiple x terms, get all of the x terms on the same side. And then your trick is to factor out that common x. So you have 2ln 5 equals, you're taking out the x. You're factoring out the x from both terms. What are you going to have left? When you take out the x here, you'll have an ln 3 minus here. When you take out the x, what are you going to have? Okay, 2 ln 5. Good. We have x. This is a messy decimal number, but it's still just x times a number. What undoes that multiplication? So here we're going to have to divide by that entire ln 3 minus 2 ln 5. Divide by ln 3 minus 2 ln 5. So on the right side we have an x equals, and on the left side, here's the stuff you're punching in. 2 ln 5 all over ln 3 minus 2 ln 5.
Why don't you use some scratch paper and think of punching in 2 plus 8 over 5 plus 5 in your calculator.
Okay, so Tony thinks we need to think, here's my scratch paper. We want to punch in 2 plus 8 all over 5 plus 5 in our calculator.
How would I punch that? We know the answer is what? 2 plus 8 over 5 plus 5. What should the answer be? 1.
10 divided by 10.
How do I make the calculator give me a 1? If I do this.
No, that's wrong. 2 plus 8.
2 plus 8 divided by 5 plus 5.
Are we getting 1?
What's wrong there? I got 8.6. But we know it should be 1. What do I need to do to make the calculator give me the right answer?
If you have a fraction that you're trying to punch in, what you want it to do is you want it to simplify the numerator, the way we did that and got a 10. We want them to simplify the denominator. The last thing you want them to do is to do what? Divide. To make sure your calculator's doing what you want it to do, you need to enclose parentheses around the numerator and the denominator. If you have a fraction that's anything other than something divided by something, this one right here, it was ln 5 divided by ln 3. There was no additional plus, minus, times, or division. And so I didn't do this. But if I have a fraction, a messy fraction, we have multiplication, 2 times ln 5, we have that subtraction. To make sure your calculator does what it's supposed to do. What it needs to do is simplify the numerator, then simplify the denominator, and remember the order of operations says you do those parentheses first. So it's going to simplify the numerator, simplify the denominator. The last thing your calculator is going to do is perform that division. So now if your calculator is like ours, it's going to also put parentheses around those numbers as well. So hold on, you're going to have to put parentheses around those as well. Punch it in and realize with our calculator what's really going to be punched in, when we press the LN key, it's going to open a parenthesis. We're going to have to close a parenthesis.
If you don't punch in 2 parentheses right here,
your answer is going to be wrong. That 5 there, when I punch an L in, it's going to open a parenthesis. I need to close it. So we're going to have nested parentheses here.
Close, that's the red parentheses. Close, that's the green one. If there's more than one number on top, put it in parentheses. If there's more than one number on the bottom, put it in parentheses. I see 3 numbers on the bottom, 2 on top. That's how you know you got to put them in parentheses. 3.
Close it. Minus 2 ln. Now you're going to have to type in the 5 and close the 5, and then close the denominator. Any questions there? I'm assuming they still want 4 decimal places?
Actually, I'm not sure. Let's look and see. 3 decimal places.
Pay attention to how many decimal places they want. So switch it back. That is a negative 1.51. Is it going to stay at 8 or go up to 9?
We're rounding it to 3 decimal places.
Negative 1.51, 8 or 9. 8, I agree. For my final answer. Punch that in.
Negative 1.58. They have the wavy equal signs.
Oh, I didn't put the wavy equal sign. I forgot to write it.
518.
Okay, let me have this. Okay. Oh. And okay, everyone got those punched in, that one punched in. So now we're ready for number 3. Let's write the problem down. Number 3. 6 to the x plus 1 is equal to 3 to the 2x minus 1. And I want to make a note. They want it rounded to the nearest thousandth. Well, how many decimal places is that? Tenths, hundredths, thousandths. That's 3 decimal places. So I'm going to make a note here. When we're through, we're going to round to the nearest thousandth. I'll say 3 decimal places. They want us to round to 3 decimal places again. At first glance, you might be tempted to say, oh, we can get a common base. 3 and 6. A common mistake is someone would try to write 6 as 3 squared. Is 3 squared equal to 6? No, that's 9. You can't. There is no common base for these for this problem. So we stick on our ln. We then use the power rule. We pick the x plus 1. We pick it up and move it down. So it's x plus 1. And since it's multiple terms, notice how I'm enclosing it in parentheses again. So x plus 1 times ln 6 is equal to, I use the power rule of logarithms here. That's me pick up that 2x minus 1 and multiply by ln 3. Now we have to get rid of the parentheses. We distribute, and once again, when you're distributing, do not get creative. X times ln 6 is just x ln 6 plus 1 times ln 6. I'm distributing the ln 6. 1 times ln 6, 1 times anything is anything. So just an ln 6 equals. You tell me what we're going to have on the right-hand side. We have 2x times ln 3 and a minus 1 times ln 3. Call it out here. 2x ln 3, good. Once again, don't get creative. You don't pick up an ln 6. It's just an ln 3 minus.
Negative ln 3.
Okay, that minus 1 times ln 3 gives me that negative ln 3. We have multiple x terms. Let's get all of the x terms on the same side. Oh, I like to move the terms around. I play around with it in my head to see how do I get fewer negatives. I think we'll have fewer negatives if we collect the x's on the right. Now, you can collect them on the left, but then you'll just have more negatives and minuses when you're punching in. But as it is, I think if we leave the x's on the right, we already have that 2x ln 3. Let's pick this term up, move it over. That's a plus x ln 6, so it's going to become a minus x ln 6 when I move it over. We already have an ln 6 here. What else are we going to have here? We have the ln 6. What are we going to have here? There's something we haven't moved yet. Okay, good. Once we have all of the x terms on the same side, that's when we pull the trick. We factor out the x terms. We still have that ln 6 plus ln 3. Hey, could we write that just as an ln 9? No. We started off with ln 6 and ln 3. We should expect just to have ln 6 and ln 3s in our final answer. We'll take out an x on the right side. What are we going to have left over inside those parentheses? Call it out. I agree, 2 ln 3. We took out the x. We are left with a 2 ln 3 minus. We took out the x, so all we had left was that ln 6. And then what do we do to undo that multiplication? X times all that messy stuff. We divide by 2 ln 3 minus ln 6. 2 ln 3 minus ln 6. So that cancels out, leaving us with x equals, here's the stuff you have to punch into your calculator, ln 6 plus ln 3 all over 2 ln 3 minus ln 6. If you have a fraction with anything other than number divided by number, you need to enclose the expression in parentheses. Enclose the numerator in parentheses, enclose the denominator in parentheses. If you don't, you're not going to get the correct answer. Just like a moment ago, we punched in that 2 plus 8 over 5 plus 5. We knew we should have gotten a 1, but instead we got an 8.5 or something, because you didn't tell your calculator. We didn't tell the calculator, simplify the numerator, simplify the denominator, and then divide. That's what we want our calculator to do. We want them to simplify the top, simplify the bottom. The last thing we divide, the operation is the division. So let's punch this in. Wait, there is too many there. Okay, there. Clear. Left parentheses. ln 6. What do I have to do? Close the parenthesis around the 6. Plus ln 3. I have to close that parenthesis after the 3. What else do I have to do? I'm through with the numerator. No, before I divide, okay, I'm going to have to close parentheses again. Basically, here's what we're entering. We have a lot of nested parentheses there, okay? So, there's what we're typing in. So we have a close of parentheses again. All of that stuff that I've typed there is the numerator. Divided by, now I have to type the denominator. Left parenthesis, 2 ln, we have a 3. Notice it opened the parenthesis, so I have to close it. Minus ln 6, close the 6, close the denominator. Any questions on how we've punched this in? Equals, and they want it rounded to 3 decimal places. 3 decimal places, so that would be I'll put the little wavy equal sign. That's a 7.12. Is it going to stay an 8 or go up to a 9? What's that digit after the 8? It's going to go up to a 9. 5 or higher, it goes up to a 9. Oh, wait a minute. That's no good there. There it is, 7.129. Any questions there? Caleb, with that nice calculator of yours, do you have to, I didn't look at it, Tony looked at it. Does it open the parenthesis when you type the LN key? Yes, and you have to close it? Okay. So, 7.129. Any questions there? Okay, number 4. E to the negative 0.71 t power is equal to 0.03. Negative 0. Yes. And they want it rounded to 4 decimal places. They say to round to 4 decimal places, and I'm going to make a note of this so I don't forget. 4 decimal places. And make sure I didn't miscopy. I didn't. So there. Let's move that calculator out of the way. The last problem we did on Monday, the last problem in the homework from Monday was important relative to in relation to this problem here. Well, think about what we're going to have to do. We have to introduce an ln on both sides. What about this ln e to the negative 0.71 t? Does anyone remember what we were saying there at the end of class on Monday? That's exactly what we said. When they're performed consecutively, they're inverse functions. They cancel each other out. That's why we had this number 20 here in the previous homework, because I knew ln e, you'll need to remember, this is easier than the other ones we've been doing. ln e cancels out, they're inverse functions, so all we're left with, we don't have to use the power rule here to bring down the exponent. It automatically just drops down because the ln e cancels. A negative 0.71 t is equal to an ln 0.03. What do we do to get t by itself? There's not multiple variable terms. We don't have to move the terms around. There's only one thing we need to do to get t by itself. Divide, that's negative 0.71 times t. To undo that times, I agree, you're going to have to divide. So, that cancels out, giving us t equals, on top we have an ln 0.03, and on bottom we have a negative 0.71. Do we have multiple operations here? An operation is addition, subtraction, multiplication, or division. Realize this is not addition. This is just a negative. Do we have multiple? What's the only operation in this entire expression here? ln 0.03. What does that fraction bar mean? Division. That's the only operation is division. So you can punch it in without introducing those parentheses around the numerator or the denominator, and you should get the correct answer. But just for consistency, I'm enclosing the top and bottom in parentheses, and when I hit that ln, what's going to happen? When I hit that ln key, it's going to open a parenthesis, so I'll have to close a parenthesis. So I'm going to have two parentheses, so I'll have two pairs of parentheses on top, one on bottom. That's going to give me, and I put the little wavy equal sign, that says this number is an approximation. I'm not going to write out all the digits because those digits, oh wait, what am I doing? There, just leave it right there. Okay, so left parentheses, ln, it opened a parenthesis, 0.03, close, divided by, left parentheses, negative 0.71, close. Once again, like on this calculator, if you don't close the final parenthesis, it'll close it for you. But as a former COBOL programmer, I know what dangling parentheses can do. I know the damage they can do. They can cause literally thousands. One dangling parenthesis, a parenthesis not closed in a COBOL program, could lead to thousands of fatal errors. So, any programmers in here? Yes, no, 4.938. 4.938. Is it going to stay an 8 or go up to 9? Does it? After the second 8? Okay, it stays an 8. Good. There. Any questions? You know something? A Sharpie, okay. There. Let's punch this in. Any questions on getting that punched in, first of all? Any questions on how the ln e canceled out? Okay. E and ln are inverse functions. When performed consecutively in either order, they cancel each other out. Any questions there? Now, logarithmic equations. There and there. Logarithmic equations. With logarithmic equations, you're going to need the equation in the form single logarithm equals a number.
Like we did the last time.
Procedure. You'll have to use your skills at condensing logarithms. If there's multiple logarithms, you'll have to use your condensing skills from the last time to write the equation in the form. We write equation in the form single logarithm equals a number. Need a single logarithm equaling a number. Then, if you think about it, it's really quite brilliant to solve an exponential equation. What were we using? We were using logarithms. To solve a logarithmic equation, what are we going to do? What are we going to use? We're going to use exponents. Remember, exponents and logarithms are inverses of one another, so it makes sense that you have to write your equation in the form single log equals a number. Then that stuff that we have there will be turned into exponents. You'll use the base of the logarithm as the base of the exponent to cancel out the logarithm. I'll say use the logarithm base as the base of an exponent to cancel out the logarithm. We even did this the last time on, well, let me give you time to write that down. But I remember working a problem where, okay, we said we're going to pretend all this stuff is exponents and the base is the base of the logarithm, and it canceled out that logarithm.
Number 3 or 4?
I think so. Let me look. Gosh, that was a long assignment the last time, wasn't it? Hey, do y'all remember this here on number 4? This was number 4 the last time. And it's in the form we need. A single logarithm equals a number. We said, okay, the base of the logarithm is a 3. All of that stuff is about to become powers, and we stuck on a common base. We're using that common base method in reverse. The common base method says if the bases are equal, the powers have to be equal. Now we're saying these are equal powers, so apply the equal base. And the base you use is the base of the logarithm, so the thing cancels out. Just like this one here. The base of the logarithm was a 2, so we turned all the original stuff into exponents using a base of 2. The logarithm canceled out. Look at that number 5. That number 5 is a good one.
Yeah.
Log base 4 of 2x minus 2 is equal to 3. Notice they're not telling us how to round the answer, because for logarithmic equations you should be able to get exact values. You don't need, you won't be rounding to get your final answer.
So that sort of gives you a hint when you got to punch the stuff into the calculator and stuff. Okay.
Yeah, if it doesn't tell you how to round, that's saying you do not use your calculator and get a decimal equivalent. You should be able to get your answer, an exact answer, without using a calculator. Okay, this is in the form we need. Single logarithm equals a number. The base of that logarithm is a 4. We're turning all of that black stuff right there into a power, or into powers. 4 to the log base 4. They're inverse functions, performed consecutively. They cancel out, leaving you just a 2x minus 2. Now on the right it looks weird, but that's saying 4 cubed. 4 times 4 times 4 is 64. Any questions on my logic there? There, if you punch it into your calculator, you see you get 4 cubed is 64. Now it's a simple enough matter to solve for x. What will we need to do? Okay, we'll move the 2 over. So we have 2x equals 60, 66. 64 plus 2 gave us 66. And then to give us x equals 33. There is one problem. We said when we started this logarithm discussion, we said the base of a logarithm has to be positive and it can't be 1. A positive number to any power is going to have what sign? A positive raised to a positive exponent. Can that result be negative? A positive to a positive is always what sign? Positive. You need to make sure. We started off with a logarithm. We wound up solving something that wasn't a logarithm. You need to make sure that the number you get gives you a positive argument as well. Well, that's what, 66 minus 2. That's obviously positive, so we don't have to worry. 33 is an acceptable answer.
So you don't really have to check it completely, but you do have to plug the number in.
And make sure that any argument that appears in the original problem is positive. So I'm going to say note. Once you solve the equation, make sure your answer gives a positive argument. Remember, the argument is the thing that comes after the logarithm. And there will be
That's
some
not
times...
a t, that's a positive.
You're right. I'm being lazy. I'm going to mark that out and write out the word. This is, when working with logarithms, that's no time to be lazy. You're right.
I'd better go ahead and plug in 33. How long?
Oh, type in 33.
Type in 33.
Mm-hmm.
33. Now, if it is given a negative argument, you'd have to choose not a real number.
Okay. Next question. You need the equation in the form single logarithm equals a number. So let's look at the next one. Number 6. Log base 8 of x plus log base 8 of x minus 12 is equal to 2. And notice once again, they don't say that you're rounding your answer. You're not going to be punching in and getting a decimal approximation. That's what you do for those exponential equations, not the logarithmic equations. We use logarithms to solve exponential equations. We use exponents to solve logarithmic equations. We need our equation in the form single logarithm equals a number. Oh, wait. Okay. We need the equation in the form single logarithm equals a number. Well, we have the equals a number part right there, but we don't have a single logarithm. The right-hand side, it'll stay as it is, the equals 2, but we need a single logarithm here. We have to write our log base 8. We're going to condense. What I normally ask when we're condensing logarithms, I would ask, do I need a fraction bar? And in this case, y'all's answer is no. Well, wait a minute. I see a minus sign right here. Why don't I need a fraction bar? The minus sign in the argument doesn't matter. It's the sign in front of the logarithms. The sign in front, that's a plus. That's an assumed positive there. They're being added, so no fraction bar. You're not dividing. There's only two things you can do to arguments. If you're not dividing them, what are you going to have to do? Multiply. You're going to have to take x times x minus 12. X times x minus 12. Any questions on our logic? Y'all remember doing this the last time? And now we have the format that we need. We have a single logarithm. So what exponent base am I going to use to cancel out that log base 8? I'm going to turn all of this black stuff here into exponents. What will be the base of the exponents? The same as that subscript there, 8. 8 to the log base 8, and that's an 8 squared. It looks funny, that 8 squared, but that's saying 8 squared, and we know that that's 64. What's going to happen on the left side? Okay, good. You're just dropping down x times x minus 12. Uh-oh. This is going to be quadratic. X times x, that's x squared, minus, what's the other term? 12x. Whether we solve by factoring or the quadratic formula, what number do we need over here? A 0, so let's move that 64 over. Minus 64 is equal to 0. It's been a while since we've had to factor. It seems like it has. Yes?
But then I was answering having so.
X squared, we know that that's x times x. Hey, look at that last sign. What do we know about the signs in the parentheses? 1 plus, 1 minus. I'll write that plus, minus. I'll wait to fill it in. Now for 64, when you think of 64, at least when I think of it, I think 8 times 8, but that's not going to do it. We could have 1 times 64, or 2 times 32, or 4 times 16, 5, 6, 7, 8 times 8. This is a simple trinomial. So in this case, you want the pair that subtracts to give you what number? 12? Okay, so it's going to have to be the 16 minus 4. That'll give you 12. Play around with it in your head. I'll write down the 16 and the 4. You tell me, what are we going to have to put here? The negative here and the positive there? Let's check. What's the outer product? X times 4x. Here's my scratch paper. That's a positive 4x. What's the inner product? Minus 16x. 4 minus 16 is a negative 12. Is that what we needed? Yes, it is. So we set each factor equal to 0. Here we are near the end of the semester. I said factoring wasn't going to go away. I said that at the beginning of the semester. I certainly wasn't lying to you. Oh, so we got x minus 16 equals 0, which means x is equal to 16. X plus 4 equals 0 means x is equal to negative 4. But remember, a step after the logarithm must be positive. 16, I think 16's okay. Put a 16 there, that's positive. 16 minus 12, is that positive? So 16's an acceptable answer. What about that negative 4? Right off, you put a negative 4 there, is that positive? Negative 4 minus 16 minus 12 isn't positive either. Discard negative 4. Suppose we'd gotten x equals 2. Would 2 have been okay?
Would here, but what about there? Sometimes students decide, oh, what he's saying is mark out the negatives and keep the positive. No, no, no.
You could wind up with 2. You've got x equals 2. 2 minus 12. No. Or 5 minus 12. Suppose we'd gotten x equals 5. Would 5 be circled or would we mark it out? 5 minus 12, is that positive?
What if we've gotten x equals 11? 11 minus 12?
Is that positive? So sometimes you may have to cross out a positive answer. But generally, if you have one positive and one negative, in most cases, the negative will be discarded, the positive will be the
if you found
acceptable
yourself
solution.
Circling the negative and marking out the positive, I'd look back over my work because that doesn't usually happen, but it could.
Yes, it
can happen in rare cases. Now let me go punch it in.
What would happen if it was like 12?
12, it would not work because 12 minus 12 is 0. 0, I'd say that it has to be positive. 0 is neither positive nor negative. It has to be bigger than 0. Okay?
And your calculator will show you that because if you punch log 0,
it doesn't matter what the base is of the logarithm. The log of 0 is going to give you an error. That argument has to be positive because a positive number to any power will always be positive.
After all of that, I forgot. What was it? 16. Okay.
Okay.
Any questions?
I know. I always took it for granted.
Yeah.
I took it for granted. If they've removed that so it doesn't show the question number, I'm going to have a problem getting used to that. The log of 6x plus 3 is equal to 1 plus the log of x minus 3. You know something? I'm going to write it up here. I write so big, I'll run out of room. The log of 6x plus 3 equals 1 plus the log of x minus 3. Okay, so
Which
switch over.
calculator did I look at it? And it actually writes out log base 10. Remember, for our purposes, if there's not a base stated, a subscript, we assume it's a 10. And that just, it's been like that for years, I mean forever, because it used to be hard to type subscripts. Not anymore, but...
Okay, switch to my page. Okay, there. Oh, that look. You know something? Can y'all tell that's a 6x?
Looks like a smear to me.
I know. Okay, I'm going to work it here after all.
Oh,
Okay, I'll just do it here. Okay. We know we need the equation in the form single logarithm equals a number. Here, we had the two logarithms on the same side. We were able to condense to get a single logarithm, and we got the number on the right. Well, I can get the number on the right by picking up this second logarithm and moving it over to the left. So I'm going to have the log of 6x plus 3. I'm going to pick that up. The only thing that's going to change is that sign in front. I'll subtract the log of x minus 3 from both sides. The only sign that changes is the sign in front. The argument just stays in x minus 3. And on the right hand side we have a 1. Can y'all read that? It's those dangling, those curvy tails of the g's. Oh goodness, that's the problem. So now we have the equals a number. All we have to do is write this as a single logarithm. There's my log. We're condensing. A moment ago I asked, do we need a fraction bar? And y'all said no because of that plus. I'm going to ask the same question now. Do we need a fraction bar? Yes, because of that minus right there. The minus in front is what says we need a fraction bar.
in the middle.
I guess you're right. Yeah, the minus in the middle. What's on top? 6x plus 3, I agree. What's on the bottom? X minus 3. I think this is the format we want. We wanted a single logarithm equals a number. That's what we needed.
Don't let the fact that there's a fraction here scare you. I think it works out.
Yeah, it works out really good. You're right.
No factoring at least.
Yep, no factoring. What are we going to... All of this stuff here is about to be turned into exponents. What am I going to put here and here as the base?
Don't see it. So what do
If
we
you see
assume?
LOG and no subscript, what do you assume that subscript is? 10. So we're now going to use a 10 as our base on both sides. 10 to the common log cancels. That leaves me 6x plus 3 over x minus 3 equals 10 to the first power is 10. I think I'm gonna do something. I'm gonna see if y'all can tell what I'm about to do. I'm gonna think of that 10 as a 10 over 1. What do you think I'm gonna do to solve this equation? Okay, so cross multiply. We go 6x plus 3 times 1. Oh, that just stays as 6x plus 3 equals, I'm running out of room, so we're going to have to do this distribution right here in our head. 10 times x minus 3, what's that going to give me here? Good, 10x minus 30. And let's move the terms around in a way so that we decrease the number of negatives. How about we move that 6 over and combine it with the 10? What are we going to have to do? That's a positive 6x. So 10x minus 6x, that gives me a 4x. Let's move this number over to the right by doing what? That'll become a positive 30. 30 plus 3 gives me 33. And then divide by 4 to give me x equals 33 over 4. But remember, we said each argument has to be positive. That means bigger than 0. Well, 6 times a positive number will be positive. Plus 3, that's positive. The exact value doesn't matter. Just verify that that argument is positive when you plug in 33/4. I'm not going to go through the tedious multiplication. 6 times a positive number plus 3 is going to be positive. Well, 33/4, that's what? 8 1/4, if you think of it as a mixed number. So it's bigger than 8. Bigger than 8 minus 3. Is that positive? Yes. So 33/4 is an acceptable solution. You can save yourself time. You don't have to, the exact value in the argument doesn't matter. Just convince yourself that when you plug that in, it'll be 8. Something bigger than 8 minus 3, it has to be positive. Any questions on our logic there? So let's punch in our answer. Oh, if it had turned out to be negative, that's when we would have selected the solution as the empty set. But 33/4 is an acceptable answer. Any questions there? Okay, number 8. Hold on, let me mark this out here. We're doing number 8 now. Log base 5 of x plus 10 plus log base 5 of x minus 10 is equal to 3. Log base 5 of x plus 10 plus log base 5 of x minus 10. Okay. Well, are we going to have to move terms around the way we did on number 7? We're going to have to condense. I know we're going to have to condense, but are we going to have to move the terms around to get equals a number like we did on number 7? Let me reword my question. No, because we already have the equals a number. We're going to have to condense, so those things are going to have to be combined, but the equals 3 is fine. We'll leave it like that for the time being. I'll write my log base 5 Here goes. We're condensing logarithms. First question, do I need a fraction bar? No, we're not dividing. If you're not dividing, there's only one other thing you can do to arguments. What is it? Multiply. You're going to have to multiply x plus 10 times x minus 10. So we're going to multiply x plus 10 times x minus 10. Has that thing been flashing on and off always?
Well, I don't know. Today it is.
I know. Every time it goes off, I panic. Okay. And here's the format that we needed. A single logarithm equals a number. We don't have log plus log or log minus log. This is a single logarithmic expression. Now, we want to cancel out that log base 5. We're going to turn all of this stuff into exponents. What will I use as the base of the logarithm? Okay. 5, I agree. The right looks funny. 5 cubed. What is 5 times 5 times 5? Don't say 15. Okay, that's 125. I agree. Realize that's 5 cubed. It looks funny just because the exponent's written so big, but I'm just a big writer. And then 5 to the log base 5 cancels. What are we going to have to do with this x plus 10 times x minus 10? Starts with an F. Not the factor word. Foil it out. We're going to have to foil that out. Okay, then we'll probably have to factor once we do that, getting it set equal to 0. But for the time being, here goes. First, outer, inner, last. I agree. That's it. Okay, so negative 10 plus 10 goes to 0.
Actually, I don't think we're going to have to factor.
We haven't used the square root method in a long time. Let's use the square root method. All we have is just a quantity squared. We don't have any variable terms remaining. The negative 10x plus 10x canceled. Let's move that 100 over. What's that going to give me? X squared equals, we have a 125 plus 100 to give me. And remember, when you're using the square root method, you drop the square on the left and you pick up a plus minus square root on the right.
They always forget to do that plus minus.
If they do forget the plus minus, this time I think they'll be okay. What's the square root of 225? That's a perfect square of 15. Now, if you'd factored it, x squared minus 225, it would have been the difference of squares. It would have factored as x plus 15 times x minus 15, and you would have still gotten two possible answers. But let's see. 15. 15 plus 10, is that positive? 15 minus 10, is that positive? Yes, so 15 is an acceptable answer. What about negative 15? Negative 15 plus 10, is that positive? No. So we don't use the negative, only the positive. And like my brother just said, come on, be honest. Most of y'all would have forgotten the plus minus anyway. Am I right? Some of y'all would have forgotten it, and if you had, you would be okay. You have to discard the negative number anyway. So the only acceptable solution is 15. Any questions on our logic there? You cannot have log plus log or log minus log. You need a single logarithmic term equals a number. Let's look at number 9.
Number 9 is a strange looking problem.
Okay. Log base 8 of log base 8 of x is equal to 0.
Do y'all see how this differs from the other ones? But it says log. It's not plus. It's not log plus or minus another logarithm.
Okay, switch. It's the way that I've written it. Notice the thing on the inside I tried to write as green. It looks black to me. Maybe I'm going. I should have used red. You're right, but still. I claim we already have the equation in the form we need. We need single logarithmic term equals a number. You can't have log plus log. You can't have log minus log. So it's already in the form that we need. I like Tony's suggestion. Log base 8. That green just doesn't show the way I want it to. Just the red. I claim we can get rid of this outer log base 8, the one that I wrote in black, by turning everything into exponents. And then 8 to the log base 8, they're inverse functions, they cancel out, leaving you that red stuff that just drops down. Log base 8 of x equals, what have we got on the right side? Be careful. 8 to the 0 power, be careful. 1, okay, good. 8 to the 0 power is defined to be 1. Y'all see what I'm going to do now? What can I do to get rid of that the red log base 8? Okay, so I'm going to do the same thing I did here. I'm going to take that base. I suppose it would have been a better problem if these two numbers had been different. Do you see? Those numbers could have been different.
But if they had been, I'm not sure when that would ever happen. When do you use two different bases on logarithms in real life?
Oh, I didn't know that we were involved in real life here. I thought we were engaged in abstract thought.
But then if that's it, then okay.
What's going to happen on the left side? Here. Okay, the 8 to the log base 8 cancels, leaving us x equals, what have we got on the right side? 8 to the first power gives me 8. That argument right here has to be positive. You take that 8 and you put it in there. Is the argument positive? Yes. So 8 is an acceptable answer. Any questions there? You know, it's hard to tell, but this is an 8.
And after that, doing that problem, I was sort of afraid that y'all were going to get all sorts of bad ideas about what we've been doing. So the next problem
is back to a traditional logarithmic equation. Say, move
sure
that in, it's exactly the same.
Oh. We've already done this problem.
Haven't we done that? That's number 6. Yeah, that was number 6.
Oh, wow. Yeah, this
okay,
problem.
Let's change it.
Okay.
There.
Oh, let me close that.
Ah, here's a good one.
Yeah.
Okay,
Here's
number
a
10.
new number.
10.
Number 10. I don't want y'all to decide, oh, well, heck, all we got to do is put 6s everywhere and get rid of it. No. Hopefully you see how this one's different. It didn't say log. This is back to logarithm plus.
Log plus log or log minus log, you have to condense. Log base 6 of x plus log base. Okay. Oh, goodness.
Well, you know, Tim, looking at this, your work for number 9,
It's
I
so
have to
messy.
say,
I
that
did a
makes
good
it
job of
completely
making-
clear to me.
I did a
If I
good
didn't
job
know
of making it
anything
look
about
messy.
them, if I looked at that, that would make it, doesn't that say everything you need to know? Just looking at this mess right here.
No one likes a smart aleck, Tony.
No,
Y'all
I mean,
tell me.
If it would look like that if I did it. I'm just saying, looking at the finished product doesn't help much.
I don't know
does
if it looked like mine, though. I mean, because I won all those penmanship awards, and I don't think your penmanship won any awards, did it?
I did win once.
You did win once.
I did win
remember.
once in my class.
Okay, I'm waiting for y'all to tell me. There's only one correct first step. What are we going to do?
Starts with a C.
We need it in the form single logarithm equals a number. We already have the equals a number on the right side, so I'm going to write my equals 2. What are we going to have to do on the left?
Not expand.
Condense? Okay. We got to write this as a single logarithm. I'm going to write my log base 6. Do we need a fraction bar? No, so if we're not dividing, the only other option is to multiply. So we're going to multiply x times x minus 5. We now have it in the desired form. We now have it in the form single logarithm equals a number. So I'm ready to cancel out that log base 6. What do I need to do? Bring it down. I'm going to bring it down as a base. Okay, I see what you're saying. 6 and 6. 6 to the log base 6. The exponential function to the base 6 and the logarithmic function to the base 6 are inverses, so they cancel themselves out. So we have, let's go ahead and distribute this right now. Call out what we have here on the left side. X squared minus, and what have we got on the right side? 6 squared. Once again, it looks funny because the exponent's written so big, but that's saying 6 squared is 36. It's quadratic, so we better get it set equal to 0. We have x squared minus 5x. What are we going to have beside the minus 5x? Minus 36, I agree, equals 0. X squared, that's x times x. What do we know about the signs? We're going to have 1 plus and 1 minus. Now 36, normally we think of 6 times 6, but no, it's not we're not going to use that one, I'm sure of that. 1 times 36, 2 times 18, 3 times 12, 4 times 9, or 6 times 6. It's a simple trinomial, so choose the pair that subtracts to give you. Okay, so you're using 4 and 9 to give you 5. Okay, I'm going to put the 4 here, the 9 here. Y'all tell me how we're going to need the signs. To give us back a minus 5x. Okay, a plus 4 and a negative 9, and I agree. The outer product, here I'm checking my factoring. X times negative 9 is a negative 9x. The inner product, 4 times x is a positive 4x. Negative 9 plus 4 gives us a negative 5x. Is that what we needed? Yes, so we set each factor equal to 0 to give us x equals negative 4, x equals positive 9. Do they both check? Which one checks? The 9 checks. 9 is positive, 9 minus 5 is positive, but right off, negative 4. Negative 4 minus 9, neither of those is positive.
Negative 4 minus 5.
Negative 4 minus 5. Discard negative 4. The only acceptable answer is positive 9. Any questions there?
So positive 9. Oops. I don't think we had any empty set problems.
No.
Did we? Okay.
Realize that you're using logarithms to solve the exponential equations. That's when you have to use your calculator and get a decimal approximation. You're using exponents to solve the logarithmic equations, and you don't have to use your calculator. You're not getting decimal approximations. You're getting exact values for the logarithmic equations, and I think that's it.
Yeah, I think number 11. Oh, one of my favorite problems. The domain of f is equal to the, do y'all remember that? The way you're switching the x's and y's with inverses.
The domain of f is equal to the blank of f inverse, the range. So, and the range of f, the original y's, are equal to the domain in the inverse function.
Someone says, say something algebraic. There it is. Domain of f is equal to the range of f inverse. The range of f is equal to the domain of f inverse.
That thing's tilting even more, I think. I'm beginning to worry about that.
Okay, well, anyway. So starting with number 11, it is...
Just review material. Now, any questions? Okay, let's stop recording, and then we need to talk about what's coming up.